Hey everybody. So we're going to do a little bit work on polar coordinates. So this video is just going to be a review of polar coordinates, which you've probably seen at some point, but maybe it's been a while and maybe it was never that much. So we'll do a little work on that, and then in the second video we'll start pulling that and relating it to parametric equations and some calculus we can do with our polar coordinates. Okay, so let's just start by a very basic idea of what polar coordinates are. Right, you're used to things like, you're used to rectangular coordinates or Cartesian coordinates where you get an XY pair and those tell you, right, so these tell us the horizontal distance from the origin, right, and the y is the vertical distance from the origin, right? So that's what we're most familiar with, right? It's a way of locating a point in the plane. So with polar coordinates, we still get two numbers. We usually use r and theta for these numbers. And instead of telling us the horizontal and vertical distances, what r tells us is the distance from the origin, and theta tells us the direction, right? So it's, instead of telling somebody, you know, if you're trying to point out something in a room, and instead of saying it's 5 feet in front of me and 7 feet to the right, you might say it's over in that direction by about 4 feet, right? And that's telling somebody which direction and how far to go to find the thing you're talking about. So that's the idea with polar coordinates. So for example, right, here's my coordinate plane. If I were to plot the point 3 pi over 6, okay? So first I got to remember a couple things. Our convention is that when we measure our angles, we think of an angle, we always put one side on the horizontal positive x-axis, and we consider moving, opening up in the counterclockwise direction as positive. So this angle, this direction, is pi over 6 positive, meaning it's an angle about this distance. Okay, this is an approximation to pi over 6. Sorry, that angle, right? That much opening. And then the 3 tells me, okay, go in that distance out 3 units. Okay, I haven't put a scale, so I can just put this somewhere, but what this means is my distance from the origin is 3 units, whatever those units are. Okay, so our couple things to remember is theta, again, I'll remind you, counterclockwise is positive. If I had negative pi over 6, I could move in this direction. So pretend I made that exactly the same angle going down. We'd still move out 3 units. Okay. Let's look at this on a little bit nicer of a graph. Let's look at the point. Look at another point. 4 pi over 3. So I'm going to share with you now a Desmos graph. This is a nice little picture. So what this graph is doing, I guess I can't make it do any more than that. So we've got a polar graph. We've got circles at various distances. So this red circle right now is representing the distance of 4, right? It's every point 4 units from the center. And then we've got these rays pointing out at various angles. Okay, so for example, if I were to do the angle or plot the point, this point plotted right here is the point 4 pi over 3, right? Because it's on this circle a distance of 4 units from the center, and this line here that it's on is pointing out in the direction pi over 3. Okay, Another thing to point out is I could plot the point. Let's see, it would be down here. Let's plot this point. There's a couple different ways I could write this. Polar coordinates aren't really unique. One way to write it is to consider this angle is 4 pi over 3. And so this is the point 4 pi over 3, right? Again, a distance of 4 from the center in this direction. And you can see that labeled down here, that's what that angle is. However, I could also do this. -4 pi over 3. This is another convention we have, which is that if I have a negative in my distance, I point in the direction the angle is telling me, and then I just go the opposite way. So I'm pointing in the same direction as this point up here, except I walk 4 units backwards instead of forward, okay? So let's do one more way to write this down. I could also write this down by remembering this. I've got an angle of 4 pi over 3. What happens if I add 2 pi to it? Well, first of all, let's just work out the fraction. So I've got 6 pi over 3. So this is just 10/3 pi. Adding an angle of 2 pi just means going to this angle and going all the way around once. So it ends up being the same direction. So here's a third way I could write this angle. 4, 10/3 pi, okay? So that's an interesting thing about polar coordinates, is that unlike our more common rectangular coordinates, they're not unique. All 3 of these are identifying the exact same point, okay? Now, it's pretty typical to use this one, right? The one that has the positive radius and the angle given in the most convenient way, right? Usually between 0 and 2 pi, maybe you could make the argument between something like -pi and pi for various conventions, but usually some interval of length 2 pi, we often give them, and most typically 0 to 2 pi, and that would be the most convenient way to give this point, okay? So that's our polar points. So let's do something else now. Let's see how these points relate to Cartesian coordinates, okay? So let me get my notes on task so I keep in mind what I want to do. So let's start a new page. So let's say I have a point. I'm just going to look in the first quadrant just for convenience. This would work in any quadrant, essentially. There's some little things we'll have to be careful of, but we'll talk about those as they come up. There's a point, right? Now, I can describe this point using Cartesian coordinates, meaning I say how far to the right should it move and how far up should it move. Right? But I could also describe this point using polar coordinates, which means I should tell it how far, I should say how far from the center it is and at what direction. Okay, so these two things should be describing the same point. Okay, so what does that mean? Well, looking at this little triangle, it's pretty easy to see that, for instance, the cosine of theta is equal to the adjacent side. So here's theta, the adjacent side of this triangle. This, of course, is a right triangle. Is x is the adjacent side, r is the hypotenuse, and sine of theta is going to be y over r. This gives us these these nice relationships. It's right here. X equals r cosine theta, y equals r sine theta. Okay, right, and with those points, or with these equations, we can convert, right? We can convert These are very convenient for converting from polar to rectangular, right? If I knew r and theta, it would be very easy to just plug them into this and convert them to our rectangular coordinates. We'll talk about going the other direction in a minute. Let's see that in action. So let's go back to the page we were just looking at. Let's go back to that point I had plotted. Okay, so remember this was our point 4 pi over 3. Write that down. So this is the point. Here we go, sorry about that. This point here in polar coordinates is 4 pi over 3. Let's convert this to rectangular. So remember the two equations I just gave us. X equals r cosine theta, y equals r sine theta. So that means that x is equal to 4, right? So remember our polar coordinates come in the form r theta. So this is 4 times the cosine of pi over 3, and y is equal to 4 times the sine of pi over 3, right? So we simply compute, we get x equals 4 times 1/2, the cosine of pi over 3, y equals 4 times root 3 over 2. So that means x equals 2, oops, you don't need that comma, and y equals 2 times root 3. So this point in polar should have Cartesian coordinates of 2 comma 2 root 3, which I wrote it in the wrong place. Let me move my writing out of the way. So there's my polar coordinates. Here are my rectangular coordinates, right? Just as we expected. There's 2 in the x coordinate, and this is 2 times root 3, right? Desmos always gives us these Cartesian coordinates, and we can see that it matches, right? If you multiply 2 by root 3, this is indeed what you get. All right, so there's a nice conversion between polar and rectangular. Okay, all right, let's go back to that picture we looked at a minute ago and figure out converting in the other direction. So let's look at this paper again. All right, so we're going to use some more trigonometry to figure out the other direction, right? In other words, if I had the Cartesian coordinate, what's an easy way to get my polar coordinates? So one relationship that jumps out pretty easily is that we have a right triangle, which means that the radius squared, or the hypotenuse squared, is equal to the sum of the squares of the sides, right? But so I've got r squared is equal to x squared plus y squared, or you could think the square root of x squared plus y squared. Either way you want to do things, right? And we typically take the positive square root, right? Like I said, we can make sense of negative radii in this, in negative r in this conception, but it's just not convenient. So we typically take the positive r unless there's some really compelling reason. So that's how we can get r. What about theta? Well, again, we're just going to use some trig to see that the tangent of theta is equal to y over x, right? That's really our one way we can define tangent. In other words, theta is going to be tangent inverse of y over x, okay? And there's our nice conversions for, this is converting rectangular to polar, right? This is the easiest way to get back and the other direction. So let's do an example of that. We're going to do two examples because there is one little hiccup in here that I've pretended doesn't exist for the moment. So let's just take the point. Let's take the point 3, -3 in rectangular coordinates, right? Notice I have to say this, by the way, because if you've noticed when we converted them, right? For instance, a minute ago we converted a minute ago 4 pi over 3 to the point 2 comma root 3. There's just two numbers here and there's two numbers here. How do I know which one's rectangular and which one's polar if somebody doesn't tell you which one it is, right? We might recognize pi over 3 as an angle measure, but I'm just using convenient ones. They don't have to be, right? I could write the point 4, 3 as a polar coordinate, and that would be valid. And so to look at them, it's not obvious which one you're talking about. So if I have a rectangular coordinate of 3, -3, and I want to convert it to polar, let's use our equations. So r is going to be the square root of x squared plus y squared, right? Which is, let's do it down here, square root of 18 or 3 root 2. So there's our radius. Right? And let's figure out theta. That means, let's see, tangent of theta is going to be y over x, so -3 over 3, or tangent of theta equals -1, which means theta equals -pi over 4. Okay, so this is just coming from the unit circle. I don't want to go too far down the road of going through all of that explanation in this video, though I'm happy to do it in another one if somebody wants to request, though timing might take a little while on that. There's certainly plenty of resources out there if you need some. Let me write in an extra step here. This means theta equals tangent inverse of -1. That's where the theta equals -pi over 4 comes from. Okay. Okay, so this means this point has turned into the polar coordinate 3 root 2 -pi over 4. Okay. Let's do something else. Let's take the point -3 root 3. All right. Well, it's quick to see r is going to have to be the exact same distance, right? I'm going to get 9 and 9 squared, so this is going to be 3 root 2. What's also going to be clear is that the tangent of theta is still going to be -1, because instead of getting -3 over 3, I'm going to have 3 over -3, which means theta is still coming out as -pi over 4, which means somehow these are two different points, clearly. These are both rectangular points. These are the same point. This can't be right. Okay? So we have to think for a second about what's going on here. So let's graph these 2 points quickly. If I take a graph and just sketch these out. The first point, 3, -3, is down here. The second point, -3, 3, is up here, right? In both cases, we correctly surmised that the distance from the origin was 3 root 2. Right? This angle of -pi over 4 looks like this. Okay? And so this is our first point, 3, -3. So this appears to be the right angle for this point. This one is correct. The problem is inverse tangent. When we took this step, remember we took an inverse tangent. Inverse tangent of -1, there are many, many theta values that have tangents of -1. Remember, trig functions don't technically have inverses. We restrict trig functions to make them have inverses. And tangent inverse will only give us answers between -pi over 2 and pi over 2. It will give us all of our answers on this right side of the unit circle from -pi over 2 up to pi over 2, right? And it can't tell the difference if you're giving it, right, the tangent of theta of -1 from both of these points. It doesn't know which one you want. So it just always gives on this side of the circle. In other words, it's always going to give us answers in quadrant 1 or quadrant 4, right? Never in quadrant 2 or quadrant 3. So we have to be smarter than inverse tangent and say, wait a minute, I'm in the other quadrant, the one that tangent inverse won't work for. So what do? We correct our angle and bring it over here. How do we do that? We're rotating by half of a circle. I'm going to add pi. Right? So instead of pi over 4, I need to add pi to this because I'm in this quadrant over here. And so theta is going to end up being 3 pi over 4. So this point's real conversion should be this. Okay? So we need to amend our original rule. So this rule here works if theta is in Q1 or Q4. Okay. Otherwise, theta is equal to tangent inverse of y over x plus pi. This is for Q2 or Q3. Okay. So we just have to add this little correction to put it into the right quadrant. Okay. Again, I'm hoping this is somewhat familiar. It might take a little bit of review, but that's our polar coordinates. So now we're gonna complicate things as we usually do. Let's now think about a little bit of polar graphing. Okay. So when we graph in rectangular coordinates, right? If I write something like y equals x plus 2, right? We all know this is a line that looks something like this. Okay? But what we don't think about often is that what this line in this graph or in this equation really have to do with each other, or this function really have to do with each other, is that every point on this line, right, maybe this is the point 2, 4, has the relationship that its y coordinate is twice as many, is 2 units more than its x coordinate, right? Its distance vertically from the origin is always 2 units more than its distance horizontally. If we're on the positive side, it's a little different in the negative direction. Okay? In other words, each of these points satisfies this equation. Right? Well, when we graph in polar, we get the exact same thing, right? We can write a relationship between r and theta. I'm writing the simplest one that I can think of right now. R is equal to theta, right? This means every point should be the same distance from the origin as the direction it's in, right? So if my angle was 0, I should be 0 units from the origin. If my angle was 1 radian, I should be 1 unit from the origin. If my angle is pi radians, I should be pi units from the origin, okay? So in this way, we can scrape out a graph by plotting those points. Let's do a couple of points and see what we get, and then make some adjustments or make some conclusion, not conclusions. Then we'll look at a computer graph of it. So if this is my equation, I want to start by maybe plotting some points. I'm just going to do a handful here. Let's put in theta is equal to 0. Let's try pi over 2 and pi. Let's try those 3 values, right? All I have to do is copy them for r, but now I got to think about what this means. In the 0 direction, 0 is to the right, I'm 0 units from the origin. In the pi over 2 direction, I'm pi over 2 units up, about 1.6, right? Maybe I'll just put that right here. In the pi direction, which is over here, I'm twice as far as that direction, right? So you can imagine as I keep making my angle larger and larger and larger, the distance from the origin is going to get larger and larger and larger. Right? What about in the negative direction? Let's add a couple of points to this. What if I put in, so far my picture is something like this. Right? As theta is getting larger, so you can imagine rotating around, theta is getting larger, the distance is getting further and further away as we go, right? Let's think about what would happen at a point like negative pi. At negative pi, I'll be negative pi from the origin. So negative pi is pointing that way, right? It's pointing to the left. Yeah, negative pi is pointing to the left, but I've got a negative distance, so I would go to the right by pi. So negative pi would be somewhere over there, right? It should be the same distance. I didn't do it perfectly. So let's look at this on a nicer graph than what I can do. So let's go to, where are you? Should do it. All right. So what I've got here, there's a blue dashed line that may or may not be very visible lying on the x-axis right now. That line's going to point in the direction. Right now I've got my angle at -4 pi. So we can think of it, -4 pi means you've gone backwards around the circle twice, okay? And what I'm gonna do is slowly increase my angle. So we'll see this blue line rotating, and there's going to be a point on it whose distance is always equal to the angle, right? With the convention that when it's negative, it's in the opposite direction. When it's positive, it's in the same direction. So right now, its distance is -4 pi, and it's in the opposite direction. So it's off screen right now. We can see I'm slowly increasing the angle, and it will eventually, there we go. See that point that just appeared in the lower right? Right now, my angle is -9.9 radians. That dot is -9.9 units along this line, right? So my distance, my angle is getting smaller and smaller negative numbers. And so my distance from the center is getting smaller and smaller as I close in. And now I've just hit an angle of 0, and I'm 0 units from the origin. Now we're going to hit the piece of the graph that I graphed by hand a minute ago. I'm going to start increasing my angle, right? So here's a small angle. I don't know, that might be pi over 12 or something like that. And you can see that that little red dot is just slightly out along that blue line. As I increase the angle, there I am at an angle of pi over 2, and I'm pi over 2 units above the origin. Now I'm at an angle of pi, that's in the negative x direction, and I'm about 3.14. I mean, you can see just above 3 on our graph out along the circle. And as I keep spinning, the angle is getting further and further away, sorry, larger and larger, and so the point is getting further and further away, okay? So we get this spiraling effect. And this is a picture of that graph, of that equation, r equals theta, okay? And that's a pretty different kind of graph than we're used to seeing in Cartesian coordinates, right? And things like our horizontal line test and vertical line test don't apply here. It's a totally different construction, so that the intuition behind them makes no sense in this graph. This is a perfectly valid function that has one output for every input, but it clearly fails the vertical line test spectacularly. It will have infinite intersection points on the vertical line test. All right, let's do one more graph. Let's again start by hand. Okay. So let's go back to the paper. And let's now graph the function. I think I was going to do r equals, yeah, we're going to graph the function r equals 6 cosine of theta. Okay. And I'm going to do it the same way I did before. I'm going to start putting in values of theta and computing values of r. So let's just do a few values of theta. I'll do 0, pi over 6, pi over 4, pi over 3, and pi over 2, okay? So I'm just going to compute values of r for each of these. R equals 6 cosine of 0. Cosine of 0 is 1, so this is just 6. Right? For r equals 6 cosine of pi over 6, cosine of pi over 6 is root 3 over 2, so this is 6 root 3 over 2, or 3 root 3. Let's approximate that. That's going to be just a little, it's going to be near, what is that? So square root of 3 is 1.7-ish, so 3.4, so about 5.1. Just because I'm in a graph and I want to have some nice, easy approximations for these. R is equal to, so I'm going to put in the approximations up here, 6 cosine pi over 4. That's 6 times root 2 over 2, or 3 times root 2. This is going to be approximately 4.2. R equals 6 cosine pi over 3. This is going to be 6 times 1/2, or 3. And then R equals 6 cosine pi over 2. 6 times 0 is 0. Okay, so there is our set of coordinate points. Let's try to graph this equation. So what do I have? The point 6, 0 means in the 0 direction, right? 0 direction is to the right horizontally. I'm going to go out 6 units, so I'll just mark that about here. We'll call this the point 6, 0. Notice this is actually one of the rare points that the Cartesian and polar coordinates are the same. This, what I've written, means 6 units in the 0 direction, but in Cartesian it means 6 units to the right and 0 up, which lands it in the same place. So it's rare, but it happens. Our next point is pi over 6, so my angle's going up slightly, and I'm going slightly less distance away. So I'm just approximating these things. This would be something like this, 5.1 pi over 6. Pi over 4, and I'm going out even less, so somewhere about there. So my direction, here's pi over 6, pi over 4, 4.2 pi over 4. Pi over 3 is something like this, and I'm going out half the distance I went over here, so maybe somewhere like this. I get, what point was this? 3 pi over 3. And then when I'm pointing straight up, my distance is 0, right? So there are some points, and maybe I want to guess that this graph is going to look like that. Okay. Now, it might be that my sloppiness has hidden the fact that this is a perfect circle or half of a circle, maybe not. Let's look at this graph another way and see if we can determine what it is. So sometimes we might want to convert this polar equation into a rectangular equation, and we're going to use those same relationships that we had before to do that. So I'm going to do a little bit of algebra. And I noticed that there's an r over here, and I can relate r to x and y, but even easier, I can relate r squared to x and y. So what if I multiply this whole equation by r squared? I get r squared equals 6r cosine theta. Now, if you remember those relationships, r squared is equal to x squared plus y squared. So I can replace this with x squared plus y squared. R cosine theta is equal to x. This is equal to 6x. Okay. Now all of a sudden I've translated this Cartesian polar equation into a Cartesian equation. It's still maybe not obvious what it is. Let's do a little bit of algebra. Let me can do x squared minus 6x plus 9 plus y squared equals 9. So I just subtracted the 6x, added 9 to both sides because I'm completing the square on this little piece, and I've got x minus 3 squared plus y squared equals 9, which we might recognize as a circle with radius 3, center 3, 0, right? Which matches very well with the picture that's showing up here, okay? And that is indeed the equation, an equation of this circle in polar coordinates. Okay, so that's it for our brief review of polar, semi-brief maybe. I'll save the calculus part of polar coordinates for the next video. All right, thanks everybody. I will see you next time.